Hello everyone. In this video we are going to talk a little bit more about vector spaces, their axioms, some examples, and some non-examples. Alright, so here's a list of all the axioms. So again, this is for a vector space over the real numbers. So the scalars or coefficients are real numbers here, and that would be the case for us almost all of the time. And so we just have these 10 axioms. Not going to go through these in totality again. But we will discuss a lot of them later when talking about how some of these sets will fail, some of these axioms, and thus not be vector spaces. All right, so now let's go ahead and look at some examples of vector spaces. So the classical example is going to be Rn, or n-dimensional Euclidean space. And so the way we can think of this is just column vectors with n entries, where each of the entries is a real number, okay? So this one is pretty easy to prove the axioms for. I want to focus on things that don't look like column vectors, since that's kind of how we usually think of vectors anyway, and why vector space seems to make sense. So let's see some things that behave similarly, but definitely don't look like column vectors. Okay, so our first example of that will be this script p sub n. So these are polynomials of degree less than or equal to n. And polynomials in R, so coefficients are real numbers, and degree less than or equal to n. So another way to write this in set builder notation would be something like this. So a(x) to the n all the way down to a1x plus a naught, where all of these ai's are real numbers. And one thing that we should mention here is the two operations. So the plus is just your usual addition of polynomials, and the scalar multiplication is exactly what you would expect as well, that you distribute the scalar to all the coefficients when you multiply it by a polynomial. So the next example is this script m sub n by n. These are the set of m by n matrices. Okay, so this is under matrix addition and scalar multiplication. So I will show this through just a couple examples, and we'll talk about this a bit more later when we start to talk a little bit more about matrix algebra, but let's do it for m 2 by 2. So if you have two matrices where we label the entries aij if you're in row I and column j, then if we take two of these, the addition is exactly what you would think it is based on how we treated vectors. You're just going to look at the entries that correspond to one another and add those up. So your top left entry here would be a11 plus b11. This would be a12 plus b12, and so on. Okay? And the scalar multiplication is also exactly what you would expect. You just distribute the scalar to all of the entries inside. So it just becomes RA11, RA12, RA21, and RA22. Okay? And it's pretty easy, hopefully, to see from there how you would do it for an n by n matrix. Nothing really changes. You just have more entries to deal with. Okay? So the penultimate one that we'll talk about here is the set of real valued functions, functions from R to R. So here, this just means your domain is all real numbers. Okay, so you can't have anything like the natural log, for instance, that only takes in positive values, right? We want the domain to be all of the reals, and it has to spit out a real number, okay? And so here, you define the addition of functions by how it acts on a given value. And again, it's exactly what you would expect, f of x plus g of x. And if you have a scalar times a function, how does that act? Well, it's just you do the function first and then multiply it by that scalar. Okay, so these are the two operations here. And then the last example, and definitely not the least, a very important example is just the zero vector. Doesn't matter what space I'm talking about, right? If I'm a vector space by axiom 4 there, I have to have a zero vector. And that actually is the only thing that you need. So this is the smallest possible vector space, right? You have to have at least one element, the zero vector. And if that's the only element, you are indeed a vector space. everything is pretty simple when it comes to scaling and addition, because the only thing that you can get from any operation is the zero vector back. So one thing I want to do quickly here is go back through and talk about the zero vector in all of these, okay? Because again, the zero vector plays a very important role. So in the polynomials, your zero vector is the zero polynomial, okay? And so what is the zero polynomial? Well, that's just p of x equals 0, okay? So obviously if you add 0 to any other polynomial, you're going to get that polynomial back. For 2 by 2 matrices, it's going to be the zero matrix. Basically the matrix with all entries 0. For functions from the reals to reals, so we have the zero function, right? The function that is constantly 0. You just think the horizontal line, the x-axis, right? This is your zero vector. And of course, in the zero vector space, the zero vector is your zero vector. So now I think you're ready for showing what you have to do at least once in your life, that one of these things is a vector space, okay? So here, note that I have the 2, so this would be polynomials of degree no higher than 2, so basically quadratic, linear, or constant. Here as well, just 2 by 2 matrices. The argument would be similar for m by n, and here, well, there's not a great way to make that a lot simpler. So choose one of these and go through all the axioms and show that it satisfies it. So to end this, we're going to look at a few non-examples. So this is a subset, right? It belongs to R2, so it's in the plane, but of course is not the whole plane. You could even draw it, right? X is greater than or equal to 0, so it'd be all the stuff over here, and including the y-axis. So why is this not a vector space? So it does have a zero vector, for instance. Addition is commutative, and all that stuff. But scalar multiplication is a problem, right? Because we have this condition, and we can easily multiply by a negative number to ruin that, right? So for instance, -1 times xy is going to be -x, -y. And so this is, so if we call this set S, this is not in S if x is greater than 0, which of course would be true for a lot of the elements in there. Okay, so this fails scalar multiplication closure, which is our axiom 6. All right, so let's look at another example here. So this is going to be an interesting one. So it's actually a set that we've already shown can be a vector space, but note that while this is normal, my scalar multiplication, I give this circle plus addition that is different, right? So it's normal addition in the first coordinate, but then 0 in the second coordinate, okay? So as you might expect, something is going to go wrong here, but let's think about what actually goes wrong, because we want to attack this wisely. So first of all, we're clearly going to get real numbers back. This is closed under addition. It's closed under multiplication. That's not going to be a problem. Addition is still going to be commutative because, you know, the 0 is going to stay the same, and y1 plus x1 versus x1 plus y1, not going to matter. Same with associativity. So it seems like addition is okay. Do we have a zero vector? So here is something that can go wrong. So this is axiom 4, right? The zero vector. So a zero vector would mean that we have this plus our x1, x2 gives us back x1, x2. But the problem is, no matter what we do when we add, we make this second coordinate 0. And so if you take anything with x2 not equal to 0, this is impossible, right? That it's never going to be able to keep it constant because it will always change something not 0 to 0 in that second coordinate. So this is one thing it fails, and I also want to show one other thing that it fails. So this would be the 7th axiom, right? So this says that like r plus s times some vector is r times the vector plus s times the vector. So if you look at the one on the left, you would get r plus s times, you know, your v1, your first entry, r plus s times v2, your second entry, and on the right, in most cases, so I put this, in most cases, this will not be equal, because when we do our addition, right, our second coordinate is going to be 0, and our first coordinate will match, but so long as r is not equal to negative s and v2 is not 0, then this is not going to match. So basically, these two axioms, it definitely fails, and thus is not a vector space. So this is an important example because you can see that it's not just the set, but also the operations that define the vector space. It's really both of those things together, okay? Because R2 is definitely a vector space under normal addition and multiplication. And for your second exercise, I want you to, again, consider R2 with this time a normal addition, but a weird multiplication that we define as follows. And again, because it's weird, I give it this circle dot as opposed to the normal dot. And so here you're seeing something similar, right? That we're multiplying in the first coordinate, but doing nothing in the second coordinate. And so I'll already spoil it and say this is not a vector space, and I want you to find at least one axiom that it fails. Thanks for watching.